Hello and welcome to day 1 in Modular in a Week, part 1. I say that because I quite quickly got a narrative problem with doing what I did in a day in one video. I did one kind of module each day, but I did many modules. And I think that if I had done one video for each day, it would have been really hard to follow, and I think that the part video for one video per module will be a much better viewing experience for you, I hope. So today, day 1, we are building VCOs, and this video, part 1, we are building a oscillator bank with a 4106 chip. So let's start by looking at which components we're going to need, and then let's look at some schematics. I also want to say I got my patch cables. I bought 100 for $45, I think. If you need patch cables, this is a really nice deal. It's about half the price I could find anywhere else. I'll put a link in the description to that. And once we start building our modular, I'm going to need these at least. We have one module and I'm already using 5, so it's good to have patch cables. And there are 5 colors, so there's some kind of color coding that we can do once we have a more complex setup. Even though it's not that complicated, it is still quite expensive from our point of view. Almost $14 with my very high count. I have very high prices on all my components, so this should be an absolute maximum. This is because 2 of the most expensive components are jacks, switches and potentiometers, and this one uses 12 jacks, so that is $6 just in jacks if each jack costs $0.50, which I've written. And also potentiometers, we have 6 of those, so that's another $6. So we're up in $12 in just pots and jacks, and then it's just $1.50 in the rest of the components. So it's, once you get lots of jacks and potentiometers, it gets expensive. However, so these are the values that I've used for resistors and pots and potentiometers, and depending on what you choose to use, you can use any other values, of course, but to build exactly mine, you need these components. This first oscillator I found on a site called Hackaday. It's a very nice site. If you haven't been there, I suggest you go and check it out. A guy called Elliot Williams made a series called Logic Noise, and I think it was 8 episodes or something like that, and it was just how to make noise and sound with CMOS chip, logic chips. And one of his parts in that series was making the 4106 oscillator. I believe it was the first one as well. So this is a really simple oscillator. So following the schematics and using the pin outs here, we can make our first oscillator. We begin by connecting plus voltage and ground to the 4106. The input is then on pin 1, so we connect pin 1 to the capacitor and the capacitor to ground. We also connect the rightmost pin to pin 1, and then we connect the middle pin to pin 2, which is the output. We do this because this way, when the potentiometer is mostly to the right, then you have the least resistance and the highest tone or frequency, and when you turn it counterclockwise to the utmost left, then you have high resistance between these two pins and you get a lower frequency. And to pin 2 we also connect our output pin, which should also be connected to ground. Once you've done this, it should sound, depending on your capacitor and resistor, it should sound something like this. So one oscillator on its own should sound something like this. A little bit depending on your values. When you start to hear only clicks, it's a bit low for oscillator purposes, but very good for LFO purposes. Like this, it's just clicks. And this is a bit high. Ear soaring. In the Hackaday article, he then goes on to do this circuit. So adding a diode and a 1K resistor in 2 of these oscillators and a diode and a 1K resistor in between. This is something he calls hard sync. So this oscillator is synced to this oscillator, which means that this oscillator will only oscillate when this oscillator is in the high. So if this one has a very long pulse and this one has a very short pulse, this one combined in this circuit will end up looking like this. So this waveform is only produced when this one is in the high. So that's how this works. So let's add this. However, I don't want to hardwire it. I want to have a input jack so I can choose if I want to hard sync or not. So we connect this to a 1N4148 and a 1K resistor, like so, and then we just connect it there, and ground, of course. So this way we now added a input sync jack to this circuit, and that sounds something like this. As I believe I said in an earlier video, I did buy an oscilloscope because I did most of the modules without one, but it is really good to have one when when doing these things, just to see what the waveforms look like. So let's look at this waveform now. This is a nice square wave, and when we go down it goes wider, and go up it gets closer together. Okay, so we have one here. Now let's take one of the lower ones, let's take this one, and let's hard sync this to this one. Now you see that there's a gap here, and if we move out a bit, it now looks like this. So this oscillator only sounds when this oscillator is high. So if we speed this up, these segments move closer. And then sometimes it is possible to cascade them one more. So if we take a higher pitch one, so really high pitched one, and we take this one, so now we have a few of the short ones, or really narrow ones, and some of the wider ones going on the most wide one. So it's possible to do some quite rhythmic stuff with this, even though not very melodic. So now you've done this once, now you just do it 5 more times. And if you want, you can change the capacitor and resistor to other values to get different ranges of the oscillators. And the values I've used are these. And also, before you continue, you need to add one capacitor from the ground pin up to the plus pin of 0.1 microfarad, and this is to remove some of the spikes over the power rail in this circuit when the oscillators go up and down, which on the Hackaday page you can also see in the schematics here, from ground to VCC 0.1 microfarad. You can also, if you want to lower the volume out from the chip, you can do so the output from this chip is around 5 volts, and you can, with this circuit, lower it to around 1 volt, which is more in the audio range of things. But working with in a modular, I prefer, at least in this module, to have it at 5 volts, because that way we can use this for as a gate and trigger and control voltage. There's nothing stopping you from making this circuit also, and you can have one jack here and you can have one jack here. That would also work. Then you get both 5 volts and 1 volt. And when you are done with all 6 of these, then you will have a Vero board that is a mess and probably looks something like this, depending on how much space you gave each components. I have a tendency to put everything very tightly together to conserve space on the Vero board, I guess. I don't know. You will see that all my Vero boards are very compressed, like this. And that is it for the 4106 oscillator bank that we are doing. You can, if you search online, you can find lots of other things you can do with the 4106. I even think that you can add its CV control. One really simple way I read about adding CV control is to starve it, so you can hear the phenomenon when you pull the power plug to the circuit. You will hear the pitch going up. So by having this control voltage as the power source for this one, you could, by raising and lowering the voltage that drives the circuit, you can change the pitch. Just a suggestion. I haven't done that. I'm going to use it quite a bit as a clock source. I think this was not. This is just to get you started, to start soldering and get acquainted with doing things on Vero board, if you aren't already acquainted with this. Let's also talk quickly about the front panel. As I said in the part 0, I make the panels in Inkscape, which I then send to a friend who has a laser cutter. You can have access to the SVG files if you want to do anything with them yourself. This zigzag kind of design was, so here you can see the outlines in green, and that was so I could compress the design in the vertical space, because all these on top of each other, it would have taken up too much space. So by doing this zigzag, the potentiometer didn't take as much space. Then I compressed it as much as I thought I could without them really touching each other. So here the outlines are gone, but they are just touching each other. So this is 14 HP, and then I actually managed to make it 1 HP even less by thinking that they could be slanted a bit, so in about 45 or 30 degrees angle, like that, facing each other all the way down. And that actually works, and that looks like this on the back side. And it did conserve a lot of space from the original design, which was taking up a lot more space. So with this design, as I might not use this that much, I don't want this to take up too much space, so this was a good compromise. And you never look at the backside anyway, so. And with this module we start our progress of filling our modular rack. We have still 3 more modules we're going to do today. The next module in part 2 will be voltage controllable, which this one isn't. This one is still usable in many ways, but you can't control it with CV, which you can with the next one. So if you like this, press the like button, the subscribe button, the bell button, any other button you might find there. And until the next video, bye.